Go. Okay, so the plan for today is to finish up chapter 4 on fractions. Last little topic, solving equations with fractions. Pretty straightforward, small little section. Um, Nothing really new or groundbreaking, just applying our previous equation solving steps that we had talked about in previous chapters to equations that have fractions in them. So not a super big deal as long as we're really solid with the operations on fractions. Uh, and again, if you're not solid on those operations yet, it's just one of those things that as you drill it, as you go through more and more problems, it becomes easier and easier. And then we're going to start into a new chapter, chapter 5 on decimals, and try to make it through 5.1 and a decent bit of the way through 5.2 today. We won't cover division of decimals today, but ideally we'll get through kind of what are decimals and how to add, subtract, and multiply decimals. So that's kind of the goal for today. So kind of an ambitious goal. We'll see how far we get. Note that the Examity practice exam is live now. So this it's not an exam that counts towards your course grade. It's not, not a high stress exam or anything like that. The goal of this exam, and I posted a Blackboard announcement about this too last week, so check that out for more details. But the goal of this exam really is solely to practice Examity, our test proctoring system. So remember, ProctorU is and not quite working so great this semester, so we're using the Examity system instead, which is still live. It's kind of our tried and true system, so I'm actually happy that we're using Examity. I wish we could just stick with it, but no such luck. It looks like we're switching to ProctorU at some point in a future semester. But the Examity system is tried and true, works great. And the purpose of this practice exam is just for you to go onto Blackboard, get into the Examity system, create an account, get things set up on that end, link the Examity, or we'll start an Examity session, link that to the WebAssign Examity practice exam, have the Examity browser add-on, enter the password, going through all that once. And number one, making sure that all the tech works out, that your browser works, cooperates with Examity and WebAssign and all of that, that your computer works with that your internet is solid enough to handle the streaming and everything. And also for you to get practice so that you've gone through it once, so that on an actual test day where you're maybe already a little bit stressed out about the test, you don't have an added layer of unknown, right? So this way you've gone through it once, you kind of know how the process works, you verified that everything works, and things should go more smoothly on actual exam day. So we don't have an exam for a couple of weeks still. The exam window, I think, is 2 weeks from this week for exam 2. Don't quote me on that, but I'm pretty sure that's when it is. It's on the course schedule. So there is a little bit of time, but I would recommend doing the Examity practice exam this week if you haven't already. Just because if there is something that comes up, a tech issue or having trouble getting something sorted out, that gives you a lot of time to either get that figured out, to reach out to me, pop into office hours, ask questions, anything like that. You don't want to wait until, the week of the actual Unit 2 exam to try the Examity practice exam and figure out that there's some tech issue, and now you're scrambling to figure out Examity, figure out the tech issue, get all that sorted out, and get the Unit 2 exam in all before the deadline. You don't want to be in that kind of a scramble. So do the Examity practice exam, this week, and that'll give you plenty of buffer if anything goes wrong, if you have any questions, to get that sorted out well before exam 2
I'm
or
a
the Unit 2
question.
exam. Oh, yeah, question?
Yeah, so whenever you go in to do the practice exam, it says enter password. What password would that be?
Yeah, so the Blackboard announcement has a lot more information about this, so definitely read through that, go through those links that I posted on there. So the Examity system has a browser add-on, and that browser add-on downloads with the password for the exam. So the browser add-on enters the password in the Examity practice exam on WebAssign. Yeah, so Yeah, definitely take a look at that Blackboard post. There is a link to a video from Harrisburg Area Community College. Unfortunately, I've tried several times to do this. I've tried to get a Blackboard student account. I used to have one back in the old days when we hosted Blackboard on our CCAC servers. I had a student account, so I could log in as if I was a student and go through all the processes and screen cap things and screen record things and show you exactly what it'll look like from your end. Unfortunately, we've gone to having Blackboard in the cloud, so hosted on external servers to us. And I don't exactly know why, but basically that means that I'm not allowed to have a student account anymore. So I only have my faculty account. So I'm not able to go through and show you exactly what it would look like. Yeah, but so for the uh, for the details, look at that Harrisburg Area Community College video. That should give you kind of a rough idea of how things work. And then also take a look at the other link in there was to a web page that kind of describes a lot of this stuff about um, how the add-on for Chrome works, the browser add-on, the browser extension, um, how that puts the password into whatever you need, whether it's WebAssign for our course or maybe in a different course, it's the My Lab system like My Econ Lab or something or whatever it may be. Um, so there's a lot of information in there, make sure that you go through, read the announcement, watch the video, read through that web page, and that should answer a lot of the questions about, the details and all that. But long story short, you add the browser extension into Chrome, and then that has an option to enter password, and that's how you get the password into the WebAssign system. Let's see, there's a question. Okay, yeah. So it looks like Angela has a question about entering negatives. Yeah, if you send me a either an Ask My Teacher message on WebAssign or an email with those problem numbers, I can take a look at the specific problems and then I can get you a more accurate answer. Um, if I had to guess, if you're putting a negative in and it's marking it wrong, and it, or if it doesn't let you. I'm not sure if it wouldn't let you put the negative in or if you put the negative in and it marked it wrong, but if it won't let you put a negative in, um, it might be that, the answer is not negative and it doesn't like that character being put in there. And if you put a negative in and marked it wrong, then it could be either, a negative sign issue, it could be a syntax issue of the way that you typed it in and it's not liking. So yeah, if you send me the specific problem numbers either through an Ask My Teacher message on WebAssign or email, I can definitely take a look at those and get you a little bit more of an accurate answer because I'm not sure what the issue would be. It could be a lot of different things depending on the specific problem. Yeah. Okay, but yeah, for the Examine Practice exam, shoot to get it completed this week. Again, it's kind of a low stress thing. It's not for a part of your course grade. It's there's a few dummy questions in there, but it's not like an exam that you should expect to like log in and like sit down for an hour and try to complete a difficult exam. You don't even have to complete any of the questions that are in there. I would recommend kind of clicking around, making sure that you can type things in, making sure that things just generally work right with, clicking on text boxes, typing stuff in, submitting questions, that kind of thing. Just make sure that things work correctly in the exam, and then you can submit the exam, close out the exam, and close out the examity session. But this is really just to practice the examity side of things, get the account set up and all that. So, zero stress kind of thing, and not really a math kind of thing. It's more just a procedural tech kind of a thing. And the quote of the day today, I actually saw this in a Facebook group over the weekend that I'm in. It's a philosophy group, and this person asked this question, and it at first glance it seems like a stupid question, and a lot of people were grilling him in the comments for asking this question, but it actually has a much more interesting interpretation than I initially realized. When I thought about it for a couple minutes, I thought, oh, this is actually a pretty interesting idea. So I decided to make it the quote of the day for the first 2 days this week. So the question is, if you could teleport into the future and teach your older self anything, what would it be? And the trope version of this, the common that everybody's heard is, oh, if you could go into the past and teach your younger self anything, what would it be? And the answer is usually either, well, I would tell myself what the Powerball number is or something, or it's like, you say like, what's your biggest piece of wisdom, or how do you avoid the biggest mistake that you think you made in your life, something like that. Um, so the kind of thing that makes this seem silly is if you teleport in the future and teach your older self, it's like, well, my older self knows all the stuff that I know now, plus a whole lot more. But I think it's actually an interesting statement because there are things that we knew when we were younger that maybe through life experience has maybe warped our view of reality, right? And maybe thinking back to how did we view the world when we were younger, in some sense that can be maybe a more accurate representation of the world. Maybe not in other senses, but I think it's an interesting question though. So if the young you could, move forward to today and teach the current you anything, one specific thing, what would it be? I think it's an interesting question. And I'm not asking for an answer, just, something interesting to reflect on. Is there something that, going throughout life over the last 5 or 10 or so years that maybe a truth about the world or something that you've forgotten? Okay, so on to the end of chapter 4. So 4.7, solving equation with fractions. Again, not a really big section here, just a few problems, just looking at using our same equation solving steps. We had two statements here that if A equals B, then we can multiply both sides by, say, a number C to get AC equals BC, or we could divide both sides by the number C to get A over C equals B over C. And similarly, if we have A equals B, then we can add a number D to both sides to get A plus D equals B plus D, or we could subtract a number D off both sides to get A minus D equals B minus D. So if I think if I had an equation like y plus 3 equals 5, say, kind of similar to this one, I want to isolate my variable. So I do that by subtracting 3 off of both sides. Y plus 3 minus 3 just gives me a y. And then on the right side, 5 minus 3 says that y equals 2. That would be my strategy if I was back in the integer section or the natural numbers section. Does my overall strategy change? The details might change, the details of the simplification, but does my strategy change if I have fractions, if I have y plus fraction equals fraction? Not really, it's the same strategy. I have y plus a number. I want to get the y by itself. I subtract off that number, and I better subtract it off of both sides. Y plus 1/3 minus 1/3 on the left side just gives me y by itself, so that's good. That's a success. On the right side, I have 5/3 minus 1/3. And now I just need to simplify that. I see that this is a difference. It's a subtraction of two fractions that have a common denominator. Well, I can put that together as one fraction over the common denominator. And I can answer as y equals 4/3, or maybe I want to answer as a mixed number, y equals 1 and 1/3. Either way I want to write the answer, I guess it would just depend on what format I'm asked for or how I plan to use that answer. So again, I don't think anything really groundbreaking here. If I have a question like this, solve 7k equals 14/3. Well, again, let's think if I had say 7k equals 14, no fractions apparent in the problem initially, how would I solve this? Well, I want to get the k by itself. So on the left-hand side, I divide by 7. And on the right-hand side, I divide by 7. 7k divided by 7 just gives me a k. And 14 divided by 7, that's what I end up with on the right-hand side. I see that k equals 2. If I have 7 times k equals 14, I divide both sides by 7, get k by itself, and then I simplify the right-hand side. If I have 7k equals 14 thirds, well, again, the strategy is just the same. The details, the tactics might be a little bit different. The simplification might be a little bit more complicated because I've got some fractions, but the overall strategy is the same. I have a number multiplying my variable. I divide both sides by that number. And I have k equals 14 thirds divided by 7. Now I've got to simplify that right-hand side. I've done the difficult algebra part. Now I just have to do the fraction simplification. Let me rewrite this 7 as a 7 over 1. And I note that I have a fraction divided by a fraction here. How do I handle that? I invert and multiply, or I multiply by the reciprocal. Times 1/7. I know that if I have two fractions multiplied together, I multiply the numerators, I multiply the denominators. And then I divide out any common factors. The 7 divides out with the factor of 7 and the 14, leaving me with a 2. And it looks like k equals 2 thirds. That's a proper fraction, so it stays that way, regardless of what we're looking for. So k equals 2 thirds is our answer. This was just scratch work, as was this. They were just simpler examples to demonstrate the point. If I have something like this, I want to solve n minus 1/6 equals 3/4. I have the same kind of setup, right? I have variable minus number equals number. I want to isolate the variable. I add this number. In this case, it's a fraction, but the strategy doesn't change. It's just the number that's subtracted off my variable. I add it on, and I do that to both sides. And minus 1/6 plus 1/6, the minus 1/6 and the plus 1/6 cancel. I get n equals, and then I get 3/4 plus 1/6. At this point, I've solved for my variable. I just need to simplify the right-hand side. Now, since 3/4 plus 1/6 is going to require a couple of different steps, let me actually come over here, work out what this is, and then I'll do the work in the scratch work area, and then I'll just bring the answer back over. I know that I need a LCD. I need a lowest common denominator because I don't have common denominators here. So my LCD is 2 times 2 times 3, or 4 times 3, or 12. I want to rewrite each of these two fractions as equivalent fractions with a denominator of 12. 4 needs to multiply by 3 to make 12. So I multiply by 3 on the top and bottom of the 3/4. And 6 needs to multiply by 2. So I multiply by 2 on the top and bottom of the 1/6. 3 times 3 is 9/12, plus 2 times 1 is 2/12. And this gives me 11/12. So all in all, I have that n equals 11/12 is the answer. And again, that's a proper fraction. So it stays in that form no matter what. Right. The overall strategy doesn't change. It's just the details of simplifying and so on that look a little different. Here I have an equation, p divided by -5 equals 7/15. If I have a variable divided by a number and I want to get the variable by itself, I just multiply by that same number, right? I multiply by -5 on the left. I multiply by -5 on the right. P divided by -5 times -5, those divide out, leave me with just P on the left. And on the right, I have 7/15 times -5. Now again, let's take this off to the side over here. I know that I have the product of two numbers that are opposite signs, so my answer is going to be negative. Note that I can also think of this -5 as like a -5/1, just to more clearly see that that is a fraction, 5/1. When I multiply two fractions together, I multiply the numerators and multiply the denominators. So I get negative 7 times 5 over 15 times 1. And I'll write out another step here. And see that 15 can break into a 3 times 5, and I can divide out the 5s with my equivalent fractions property. This gives me -7/3. So the overall strategy is the same as we've seen before. The main difference is that the simplification step involves simplifying some arithmetic expressions with fractions in them. And then last but not least, we have this problem, y plus number equals number. How do I solve this? How do I get the y by itself? I subtract off this number. In this case, it's a fraction, 3/8. And I subtract it from both sides. So I get y equals -2/3 minus 3/8. And again, I need to simplify this. Since it's a little bit complicated, I'm going to come off here to the side, do my simplification, and just transfer the answer back over. That way I just don't have to write y equals a whole bunch of times and make my work for my problem that much longer. So again, let's find a lowest common denominator. So 3's prime factorization is just 3, and 8 is 2 times 2 times 2. My LCD is just 24, the product of 8 and 3. I need to multiply 3 by 8 to make 24, so I multiply by 8 on the top and bottom of the 2/3, well, the -2/3. And I have 3/8. I need to multiply 8 by 3 to make 24, so I multiply 3 on the top and bottom of the 3/8. So this would be -16/24 minus 9/24, or -16 minus 9/24. Well, that's -25/24. I could leave my answer as an improper fraction if that suited me, or I can make this a mixed number, 1 and 1/24. Any questions on any of this? So again, this was a pretty quick section because we had already done a lot of work solving equations, building up these equation solving steps, these properties that help us solve equations. And the strategy is really no different. Adding in this one extra step of either, say subtracting a third here or dividing by 7 here, adding 1/6 there, etc., doesn't really change our strategy for solving equations. What changes is the simplification at the end. So the fact that we're now solving an equation is kind of irrelevant to the matter, right? The equation solving step is still the same as before. The big difference is what does our simplification look like at the end? And we might have to add or subtract some fractions or multiply or divide some fractions. And we now know how to do that. So any questions on solving equations with fractions, or really any questions about fractions in general, anything about chapter 4 in general? Okay, so moving on to chapter 5 then. Introducing this new idea called decimals, which we all have lots of experience with. Right, we deal with dollars and cents every day. So if I say something cost, 1.25, what I mean is $1.25, or $1.25 of a dollar. So we intuitively kind of understand decimals and use decimals all the time when we're dealing in currency. Let's look a little more carefully at what are decimals. And my middle column here, for some reason, keeps getting misaligned. I keep lining it back up, centering it, and it keeps getting uncentered. So let's see how long it lasts this time. Okay, so let's think first about integers or natural numbers. I have, for instance, a number like, say, 10,000. I could think of this as a fraction. Okay, well, I guess it's a lost cause. I don't know. As soon as I click on it, it realigns it. Gotta love Microsoft. I have a number like 10,000. I could think of this as like 10,000 divided by 1, right? Any whole number I can just divide by, I can put it as a fraction divided by 1. And this gets the place name of 10,000s. Right? I might have 1/10,000 or 2/10,000s or whatever. I have a number like 1,000, which I can write as 1,000 over 1, and it gets the place name thousands. Or 100, it could write as 100 over 1, gets the place name hundreds. So we see that each time we kind of go down, so to speak, a place name, we divide our numerator by 10. We kind of lose a 0 off of our numerator each time we go down 1. The number 10, I could write as 10 over 1, and it's the tens place. The number 1, I could just write as, I guess, 1 over 1, losing a 0 off the numerator again, and it's the ones place. So we're familiar with all of these places from previous work. If I want to keep going, I actually can. We might think, well, where do I go after I have 1? Because I don't have any zeros left in the numerator to lose. Well, instead of losing zeros in the numerator, what we do is we start appending zeros in the denominator. So I can look at the fraction 1 over 10. This is kind of the mirror of 10 over 1, right? It's the reciprocal of 10 over 1. The number 10, I write as the decimal 0.1. That's 1/10, and this is the tenths place. Unfortunately, it can be a little bit hard. It's kind of annoying how somebody somewhere decided to name these, because tens place and tenths place can sound quite similar when you're speaking quickly. So when it's kind of ambiguous, when we're just dealing with kind of an arbitrary number where there's no context, I'll try to be really specific whenever I pronounce these to make it very clear. But sometimes it can be hard to tell what somebody said, whether they said tens place or tenths place. But if I keep going, if I go from 10 to 1 or 10 over 1 and I lose a 0 off the numerator, to keep going, I can start adding zeros or appending zeros on the denominator. So 0.1, I put a dot there and then a 1 after it. That's 1/10, and that's the tenths place. Or 0.01, 1 over 100 is the hundredths place. Or 0.001, 1 over 1000 is the thousandths place. And 0.0001 is 1 over 10,000. It's the 10,000ths place. One's a kind of slightly unfortunate thing to notice that's easy to trip you up. And it honestly can sometimes trip me up. I have to step back and think. So be careful with this. I noticed that like I have 3 zeros here and 3 zeros here. I have 2 zeros here, 2 zeros here, 1 and 1, no zeros and no zeros. Here I have a 0 in the denominator, but I do not have a 0 in between the decimal point and the 1. So 0.1, that 1 being moved 1 digit to the right of the decimal point, is what that 0 in the denominator is doing. It's almost like the point is acting like a 0 in some very loose metaphorical sense, right? Here I have 2 zeros in my fraction, but I only have 1 0 in between my decimal point and my 1 over here. Or I have 3 zeros against 2, or 4 versus 3. So in these decimals, it's almost in some sense like the decimal point is kind of one of the zeros. It's one of the increments where we move the number past it. So in the tens, hundreds, thousands places up here, kind of the number of zeros that we see kind of in our number, the number of meaningful zeros matches the number of zeros that we see in our fraction. But down here, the number of meaningful zeros that we explicitly see in our decimal is kind of 1 off from the number of zeros we see in our fraction. So again, maybe you can loosely think of it like the decimal point is acting like a 0 here, because if we move the 1 kind of 1 unit to the right, it's kind of like moving from 1.0, it's kind of moving 1 place to the right. It's kind of passing that decimal point to go from 1 over 1 to 1 over 10. And then each time that we append another 0 in the denominator, we stick another 0 in between the decimal point and the number. So just something to be careful of. It's pretty symmetric how it works with the tens, hundreds, thousands, and the tenths, hundredths, thousandths, and so on, but not completely symmetric. So just note that little discrepancy there. Or in a more diagrammatic fashion, we have something like this, right? We have the decimal point going to the left. We have the ones, tens, hundreds, thousands, etc. Going to the right, we have the tenths, hundredths, thousandths, etc. So a really important note is that place values to the right of the decimal point are very similar to fractions. We've in fact kind of basically equated them to fractions up here. They simply represent parts of a whole. So these decimal parts are very similar to fractions. I mean, they're in some sense like mathematically equivalent to fractions. We maybe write them a little bit differently. They maybe have some different nuances. Maybe certain ideas are easier to express in decimals and other ideas are easier to express in fractions. But kind of like from a strict mathematical standpoint, they're essentially the same thing. So when we see a decimal number, we think, okay, we could work with that as a decimal or a fraction. And kind of likewise, if we see a fraction, we can often work with that as a fraction or a decimal, whatever suits us best in that situation. I might be overplaying that a little bit, but I don't think that much. Okay, so let's give the name of each of these decimal numbers. So 7.2, I have like a 7 in the ones place and a 2 in the tenths place. So this would be 7. Now, how do we verbalize the decimal point? Well, I guess if we wanted to really stick with the kind of book's way of doing it is 7 and the decimal point kind of translates as and to of what place of the tenths place? 7 and 2/10. Or what we would, maybe more often say is something like 7.2. We could really get away with saying it both ways. The way the book does it this way does have a good reason for doing it this way, even though it's a little bit less common colloquially if you're just talking about these numbers, in an application or something, 7 and 2/10. The reason the book is doing it this way is it's really driving home the idea that, well, like 2/10, number one, it's naming the place value. So it's getting us used to saying these place values and indicating what they are. And number two, I think it's also kind of reminding us over and over and over again that these really are fractions. So it's 7 and 2/10, or I can think of this as like 7 and 2/10, right? We haven't quite gotten there yet, but I think we can see that this this is kind of verbalizing it this way is a natural lead into thinking about this as, say, a mixed number or a fraction. But quite often we'll just hear people say something like 7.2. They'll just say point for the decimal point. But in this course, I'm going to try to, when I verbalize it, usually say something like 7 and 2/10. Okay, so let's look at this one. 13.51. So we look at the number to the left of the decimal point. That's 13. The decimal point we say and the number to the right of the decimal point is 51. And that's 51 of what? So that would be 13.51. I see that this is 51 hundredths, right? There's 1/100th plus, if I'm 1 to the left, that's 50 hundredths as well. So that's 13 and 51 hundredths. If I look at this example, I might actually have to count my zeros really carefully here. Here's my decimal point. I have 2, 3 zeros, and then an 8. So sometimes if I have a bunch of zeros, I'll do something like just put a line in between them. That helps kind of divide them in half and count them a little easier. I might split them off in increments of 2 so I can count them, or even maybe in increments of 3. Once you get up to where you have 4 or 5 of them grouped together, it becomes pretty hard to read. But if I kind of regroup them, I see, okay, there's 2 and then 1 more. So 0.0008, or that's 0.0008. And I see this is actually a pretty easy one. It is just 8 10,000ths. Even though it had all those zeros that I had to count carefully, writing it out isn't too bad. So it's 8 10,000ths. And what about something like this? Well, I see that this is a decimal number, 4.759, but it has a negative sign in front of it. That negative sign kind of negates the whole number, takes the opposite of the whole number, so this is negative. And then again, if I go up here, I have 4.759. So I see that this would be 759 thousandths. I can circle it without crossing it out. There we go. So 4 and 759 thousandths. 4 spelled correctly. Negative of 4 and 759 thousandths. So there's our 4 and 759 thousandths. One little minor note, back when we were talking about place names in the first place, we would pronounce something like this as 759, right? If we just had 759, we'd say that's 759. And we were kind of careful not to say 759. Well, now we kind of see why, because we've kind of like trademarked the word and to represent the decimal point. So if I said negative 4 and 759 thousandths, it's not exactly clear like where the decimal point is, right? I mean, maybe if I really went through and parsed it and said how, does it make sense this way? Does it make sense that way? I could figure it out, but it's not initially clear. So I don't want to say something like negative 4 and 759 thousandths. When I'm dealing with a number like 759, I just want to say 759. So that way, anytime that I hear the word and in a number, I know that that signifies the decimal point. I could go the other direction as well. I could write as a number, the decimal number, 7 and 354 thousandths. So I have 7 and decimal point 354 thousandths. So I have 7 and starting in the thousands, I have 354. So 7.354. Now, kind of a tough question. I won't say a trick question. It's not a trick question, but it's tricky. It's tough. What if I change this around a little bit? What if I said write 7 and 354 10,000ths? It's not going to be 7.354. I mean, pretty clearly, I changed the number. 7 and 354 10,000ths. Well, now I'm starting over here. I have 354 of these. In other words, I have 4 ones of these. I have 5 tens of these. And I have 3 hundreds of these. And then I put this 0 in as kind of a buffer. So 354 10,000ths tells me that that 4 has to land in the 10,000ths place. And then I make everything else work out right. So this is going to be 7.0354. This 0 gets stuck in there as kind of a buffer to make sure that that 4 ends up in the 10,000ths place. So you got to be a little bit careful. It's not always just, point, and then I see a 354 here. It's not just always 0.354. It does depend both on the number and on the place that's given. Any questions so far? Let me give myself a little more room here. Okay, so let's look at these examples. Let's take each of these decimals and write it as a fraction or a mixed number. So 7.35 is 7 and 35. Well, that's the 10th place, the 100th place, 35 hundredths. Or in other words, that's 7 and 35 hundredths. 7 and 35 over 100. One thing that's really nice about being able to verbalize these really carefully is it makes it actually really easy to convert to a mixed number. Right? If we think all the way back up here, this 0.35, I see 1, 2 places to the right of the decimal point. 0.01 has 2 places to the right of the decimal point. So I have 35 hundredths, or 35 of these. You could think of it as like 35 times 1/100th. I have 35 of these, or just 35 over 1 times 1 over 100, 35 over 100. Or 5.9, 5 and 9/10ths. Well, again, that's just 5 and 9/10ths. It just, we almost get like the mixed number for free if we have verbalized the number correctly. Or something like this, 0.03. 0.03, we see that we have no tenths, we have 3 hundredths. So we just say that this is 3 hundredths. 3 hundredths, or 3 over 100. One little kind of side note. It's pretty typical to stick a 0 in front of the decimal point if there's not another number there. It's not technically necessary. You could write it just as something like 0.03. But the thing is that if you just write 0.03, it's really easy if somebody's reading, if you're reading a paragraph or something and, there's a whole lot of text and then there's a 0.03 there, it's really easy to miss the decimal point. So to make it really, a bit more obvious that there's a decimal point there, we usually put a leading zero. So 0.03, something like that, or even something like 0.3. Seeing that kind of extra zero there, like if this was just the number 3, I wouldn't write it as 0.3. That would be kind of a strange way to write it. It wouldn't, again, it wouldn't be wrong, but it would be strange. But if I see something like this, I'm going to be kind of just naturally looking for a decimal point. So just to make it a little easier to read, we usually, if we just have a number like 0.03 or like this one up here, like 0.0008, we usually put a leading zero in front of the decimal point just to make it a little easier to read, to make it a little less likely that we miss that decimal point. You can also see that with multiple zeros, oops, how did I do that? With multiple zeros, it actually gives a nice break between the zeros that also kind of says, hey, there's something here, right? I have my 2 or 3 zeros, whatever, to the right of the decimal point, but they're really close together. And they're going to be further apart from the other zero. Again, that just gives that little visual indication that, hey, there's something there. Don't miss that decimal point. So we typically put a leading zero in front of the decimal point whenever there's not another number there. Like this 5.9, there was already a 5 there, so we didn't need to put a leading zero in front there. And if you use a monospace font, the decimal point is even clearer. I like monospace fonts, but pretty much everybody hates them. So, um, but if you're into computer programming, monospace fonts work really nicely sometimes. So what about a number like negative 4.75? Or this is negative 4. And so what about 0.75? We're going to take negative 4.75. This is 75 hundredths. 75 hundredths. Or this is negative 4 and 75 hundredths. Again, if we verbalize the decimal carefully, it almost gives us the mixed number kind of for free. Or negative 0.125. Well, this is simply 125 thousandths, one negative. Or it's 125 thousandths, make it negative. And then, of course, if we wanted, say, an improper fraction, well, we just convert to a mixed number and then make that into an improper fraction, right? So we could say that this is 735 100ths. 100 times 7 gives me 700 plus 35, or 59 tenths, or negative 475 100ths, right? We can convert those to improper fractions if we so desired. Any questions on these? Okay, let's look at these handful, these 6 or so decimal numbers. Let's write them in order from smallest to largest. And then let's write them on a number line. Well, the first thing I might notice is I have some that are negative and others that are positive. Well, negative any number is going to be less than positive any number. So I know that the negative 2.8 and the negative 0.01 are going to kind of go to the left. And I know, and I'm not writing these in any particular order. I know that these four numbers are going to go to the right. These four are all positive. They're all going to be bigger than those two that are negative. Now let's order these positive numbers. Well, I noticed that these two have one hole and these two have zero holes, right? So I actually know that the way I have them here looks good. The more holes is always going to be bigger than the less holes, right? WHOLE, I'm saying hole. So like a whole pizza versus no whole pizza versus two whole pizzas. The more holes that I have, the bigger the number is going to be. The larger this number in front of the decimal point is, the larger the decimal number is going to be. If I have one whole pizza and a little bit of extra pizza versus if I have a large fraction of a pizza, but not even a single whole, the one whole plus a little bit always wins out over the larger fractional part if I have no whole, right? So like one whole pizza plus one tiny little slice of a pizza is always bigger than, these are like the worst slices of pizza ever. I would be fired as the pizza cutter, but it's always bigger than, a large fraction of pizza that doesn't quite make a whole, because the whole always wins out, right? So if the number to the left of the decimal point is bigger, the decimal is a bigger number. Now let's compare each of these. So I know that these negatives are going to be less than these 0.3 and 0.9, which are going to be less than the stuff with one hole and then some extra parts. But let's compare each of these. Let me clean these up a little bit. One downside of working with decimals is that any little speck or uh, whatever, misclick or whatever, can look like a decimal. So we have to be a little careful when we're writing random stuff. Okay, so let me look at 0.3 versus 0.9. How many tenths do I have? Well, on one hand, I have 9 tenths, and on the other hand, I have 3 tenths. If I have more tenths wins out, no matter what the hundredths are. In this case, the hundredths aren't any different, or they don't show up here, but I have 9 tenths versus 3 tenths. I know that these are going to order this way. 0.3 is going to be less than, let me write it even a little more explicitly, less than 0.9. I know these both are going to be less than both the 1.83 and 1.85. Now these both have one whole. They both have 8 tenths. They're tied on the tenths. So now we go down to the hundredths. Well, the 1.85 has more hundredths than the 1.83. They're tied on the holes in the tenths. It comes down to the hundredth to make the decision. And there we go. Now for the negatives, again, I have to be a little bit careful. If I were to compare positive 2.8 and positive 0.01, I see that 2.8 is bigger than 0.01. But when I take the opposite, I kind of take that whole number line and flip it over. Things that were to the right initially end up to the left. So negative 2.8 is less than negative 0.01. If I owe somebody 1/100th of a slice of pizza, or if I owe somebody, let's just think of currency now. If I owe somebody 1 penny, then I am less worse off. I'm better off financially than if I owe somebody $2.80. So negative 2.8 is less than negative 0.01, and I can't quite shimmy that in there. Oh. So this is all of my decimals ordered. I started splitting the negatives and the positives, putting the negatives to the left, positives to the right. And then I looked at wholes versus tenths versus hundredths and so on, and ordered them along those lines. More wholes always beats less wholes, regardless of the tenths or hundredths. If the wholes are the same, more tenths beats less tenths, regardless of the hundredths or thousandths. If the wholes and the tenths are the same, more hundredths beats less hundredths, regardless of the number of thousandths or 10,000ths or whatever. We just go down the line that way. It's almost like when you put something in alphabetical order, right? Like the first letter trumps everything else. If the first letter matches, then you go to the second letter, and that trumps everything else. And if the first two letters match, then you go to the third. It's very similar to that. And if we want to write these on a number line, maybe go 0, 1, 2, -1, -2, -3. And I see I have 0.3 and 0.9 that have 0 holes and only a part of a hole. So 0.3 is maybe here. 0.9 below 1, but pretty close to 1. 1.83 and 1.85 are both between 1 and 2. There's one hole plus some fractional part. So they're in this interval. And they're both going to be really close to one another. Pretty close up here near 2. Negative 0.01, negative 1/100th. That's like really close to 0, just slightly on the left side of 0. And negative 2.8, that's between -2 and -3. Be a little careful. It's not like -2 plus 0.8. It's, if you think of where 2.8 would be, right? Positive 2.8 would be like between 2 and 3. And then we flip it over. Negative 2.8 is between -3 and -2. So it ends up in this interval. And it's going to be a bit closer to -3 than it is to -2. So we'll put it maybe something like that. So we've got everything ordered, and then we put it on the number line. It's a good idea to order it first, I think. That just keeps it keeps things more orderly when you're putting it on the number line. It helps you keep track of what goes where, I think, when you order it first and then make a number line. Not that you necessarily have to order it before you do that, but I think it just splits out those two steps of, what are the orders of the dots and then what are their locations. Any questions? Okay, so what about rounding decimals? Well, the good news is that rounding decimals works essentially the same way as rounding whole numbers. So if we want to round a decimal number like 5.781 to the nearest tenth, we have an indicated place name that we want to round to. So I want to round to the nearest tenth. So I want something dot something, and this is the tenths place. So I want to end up with some number dot something. I want to only end up with one number after the decimal place. So I find the tenths place. That's where the 7 is located. Kind of drew that arrow a little funky there. Let me draw it a little better. The tenths place is where the 7 is located. I look at the one number to the right of that, and I say, well, I'm interested in the number 8. since 8 is bigger than or equal to 5, I round up. So the place of interest, the tenths place with the 7 in it, because the 8 is a number that's bigger than or equal to 5, the one place to the right is bigger than or equal to 5. I round up, which means the 7 gets rounded up to 8. And this gives me 5.8. Or it gives me 5 and 8 tenths. When I say the number, 5 and 8 tenths, when I say the number verbally, I should be saying the place that I rounded to. Right? If I say mistakenly rounded this to 5.78, I would be saying 5 and 78 hundredths. But the place that I'm naming is not the place that I was supposed to round to. Correct. So when we round, we only are concerned with the place of interest and one place to the right. We kind of forget about all of the places further to the right than those two. In this case, in the decimal case, we just leave those off. In the whole number case, like if we had 5,781 and we wanted to round to the thousands place, thousands place now, not this place, then we would make this 5,800. So we would turn these into zeros in a whole number and they would stick around. Really, here we kind of have 5.800, but if we have 0 hundredths and 0 thousandths, then we can just leave those off, right? Trailing zeros after the decimal point or leading zeros before the decimal point, we can leave off. But these zeros are important placeholders because, of course, 5,800 is not the same as 58. Yeah, so we only look at the place of interest, to the tenths place with the 7 in it, and one place to the right. And then all numbers to the left of the place of interest just stay the same. Um, if if somebody is rounding all of the numbers, if somebody is increasing all of the numbers to the left by one, you know, in short, they're doing it wrong. I'm not sure who is doing it that way, but I can't think of any logical scenario where somebody would do that, even in like, strange types of math, like complex numbers or anything like that. It always works this way. So either that person is most likely they just made a mistake and are doing it wrong, or they're doing something in a completely different number system. There are lots of different number systems out there that can have strange operations, but that would be quite a strange number system to make up. So yeah, I think that if somebody, was teaching it that way, where if they say round up, they take all of the numbers to the left and increase them all by one, I think they probably just made a mistake there. Okay. I mean, definitely, if you have that resource, I'd be happy to look at it. And yeah, yeah, if you have that resource, if it's like a YouTube video or a web page or something, if you want to send it to me in an email, I can take a look at it and try to give a little more insight. But um, uh, my strong suspicion is that they made a mistake or they just did it wrong. Um, that would be my guess. But certainly in kind of the standard number system that we're working in, this would be the way that the thing should be rounded. Yeah. Okay, let's look at negative 1.638, rounding to the nearest whole number. So our place of interest is this 1 here. and then we see 6. So 6 is bigger than or equal to 5. So we want to round up. Okay, so if we round up, then, well, negative 1.638, we would round up. So we want to take the 1, want to make it 1 higher. And we could write this, I guess, as like negative 2.000, but most likely we just write this as negative 2, rounding to the nearest whole number. Now we want to be a little careful here. This can be a little bit confusing, right? Oh, there we go. Round up, what does that mean? We might be tempted to say something like, well, negative 1, if I increase that by 1, if I add 1 to that, it rounds to like, negative 1 plus 1 is like 0. I might be tempted to do, negative 1 plus 1, rounding up, is 0. Does that make sense to do? Well, let's actually think back to the number line. If we got kind of confused with our details here, here's 0, here's negative 1, here's negative 2, negative 1.638 is maybe something like here. Do I think the nearest whole number, the nearest one of these integer points to this decimal point, is all the way over here? No, I don't think that's right. Right. So if I did get a little bit messed up, or if I was unsure of how the rounding rule should apply to negative numbers, or I forget that a little bit, I can see very clearly that this negative 1.638 is physically closest to the whole number negative 2. It's not physically closest to negative 1, and certainly not to 0. So by rounding up, what I mean is take 1.638, round it, and then stick a negative on it. 1.638 would round up, so to speak, to 2, and then I negate that. And we can see that, that makes a lot more sense than maybe doing something like, taking the negative 1 plus 1 and making a 0. That doesn't seem right at all. If anything, if we were going to go the other direction, we should round to negative 1, but we see that this point is a little bit further away from negative 1 than it is from negative 2. So round up, I'll put in kind of, quotes. We round the number as if it was a positive number, and then we stick a negative on the front of it. So we don't want to do something like this. And we can kind of see that from the number line too. And I would argue, that's kind of a similar argument to the one up here. If I was to say like 5.781, since the 8 is bigger than or equal to 5, if I was to try to round this and say that the nearest tenth is going to be like 6.8, say rounding the 5 and the 7 by increasing both of them by 1. If I was to do something, I'm writing this in red because this isn't the right way to do it, but if I was to argue something like this, let me get a little more room here. So here would be like 5.7, 5.8, 5.9, 6.0, 6.1, 6.2. I'm way over the now, but 5.781 would be like here. What's the nearest tenth? Well, it's going to be 5.8. It's not going to be all the way over here at 6.8, somewhere way off to the right over here. That's not going to be the nearest tenth in any kind of reasonable interpretation of the word nearest. It's going to be either 5.7 or 5.8. It's going to be one of the boundaries that it's kind of sitting in between. And then we discriminate between those two on the basis of whether that next digit is bigger or equal to 5 or less than 5, whether our point is to the right of the midpoint or to the left of the midpoint in that interval. But it's certainly not going to be all the way up here at like 6 point something, or even worse, if I had like, 135.781, would I make this like 246, like adding like going like 100 units way further off to the right? Um, you know, so that's why I say, I mean, I think that person probably just messed up. Mathematics is a huge field, so I mean, it is theoretically possible that they're working in a different number system or with different definitions or something, but I think that they probably just made a mistake in how they went about solving that problem. But we can always think back to the number line to kind of make sense of things like this as well. Okay, but rounding 0.5379 to the nearest thousandth. So remember, the first place to the right of the decimal point is the tenths place, then the hundredths place, then the thousandths place. So the 7 is in our place of interest. To know whether we round up or down, we look one more place to the right. Since 9 is bigger than or equal to 5, we round up, meaning the 7 increases by 1 to an 8. I keep all of my, let me write that a little better. There we go. I keep all of my digits to the left of the 7, now 8, exactly the same. And the digits to the right, I just get rid of. Essentially, they become like zeros, but I just don't have to write them because they are to the right of the number after the decimal point. So this would be 538 thousandths. And then lastly, around 7.096 to the nearest hundredth. So I kind of wonder if maybe this is the context for that kind of doing two numbers over. So we do have problems like this one. Rounding 7.096 to the nearest hundredth, the 9 is the number in the place of interest. The next number over is a 6. I kind of didn't realize that every one of these we ended up rounding up, but we don't always round up. I should have picked one where we rounded down. But 6 is bigger than or equal to 5, so we round up, which means we add 1 to the number of interest. So I kind of want 9 to go to 10. Or I kind of want like 7.010. I want like 10 hundredths. But I know that that's not going to work, right? I can't put two digits in one place. So I kind of want like 10 hundredths. But I know that 10 hundredths is like 10 times 1 over 10 times 10. 10 hundredths is just 1/10. 10 hundredths is the same as 1/10. So I kind of want 7 and 10 hundredths, but that's the same as 7 and 1/10. So my 10 hundredths could be like 10, kind of roughly speaking, in the hundredths place, bumping that 1 over one place to the tenths place. Or we could look at our fraction to see the 10 hundredths is just 1/10. So we end up increasing the tenths place as well. The 9 increases to 10, but that kind of like just the 9 rolls to a 0 and we carry the 1 over. I kind of wonder if that was the situation for something like this. If this had been something like 5.981, we'd round it to 6.0. So that might be the case. But here our answer is 7.1. Okay, and a couple practical examples here. So Jennifer bought a dining room set costing $1,038.99. And you know that sales tax, if we say like what's 7% or something sales tax on this amount, it usually doesn't come out to be a super nice number. It usually comes out to be a number like this with a whole bunch of decimal places. Now, of course, in terms of dollars and cents, we can only pay in increments of 1 penny. I can't pay in increments of 1,000th of a dollar or 1/10,000th of a dollar. So I can only pay in increments of a penny. So I want to round to the nearest penny, or in other words, the nearest hundredth of a dollar. 1 penny is 1/100th of a dollar. So my place of interest is the hundredths place where the 3 is sitting. One place to the right of that is 4 here. Since 4 is less than 5, we round down. We finally got to round down. All the numbers to the left of 3 stay the same. Since I rounded down, the 3 stays the same as well. And all the numbers to the right, well, we could say they turn into zeros, but since these are zeros that are to the right of the number after the decimal point, we just don't write them. So this would round down to $67.53. Okay, another example. So Jim ran a 100-meter race in 12.32 seconds. Tim ran the same race in 12.3 seconds. Who had the faster time, Jim or Tim? I'll probably get it backwards because Jim and Tim sound very similar. But which of these numbers, 12.32 or 12.3, is the smaller number? Well, 12.32 versus 12.3, I see they have the same tens place. They both took one lot of 10 full seconds. I see they have the same number of full seconds. They both took 2 full seconds on top of that. And they both have the same tenths of seconds. They both took, on top of that 1 10 seconds and the 2 1 seconds, they took 3/10ths of a second on top of that. Now the second guy, who's the Tim, so T and versus J. So T has, we're tied on all of the tens place, the ones place, the tenths place. But in the hundredths place, in the hundredths of seconds, Tim took 0 hundredths of seconds and Jim took 2 hundredths of a second. So Tim won because 12.3 is less than 12.32. So Tim ran the race in 2 hundredths of a second faster than Jim did. And last example here in this section, Jerry saw a sign advertising postcards marked for sale at, quote, 10 for 0.99 cents. What's likely wrong with the advertised price? Well, 0.99 cents would be like a fraction of a penny, 99 hundredths of 1 penny. Probably what they mean is 99 cents, or that would be 99 hundredths of a dollar, 0.99 dollars. I don't know why we write cents to the right and dollars to the left, but it is what it is. So they probably mean to either write it as 99 cents or as $0.99. As another example, though, kind of leading into our next section, if you look at the price at gas stations, they're usually priced in terms of fractional cents per gallon. So if you ever see like, your gas station will have like a dollar symbol and they'll have like 3 squares that they can change the number on. This usually be like a point coded on there, and there will usually be a little 9 up here. So it might say like 325. Those are the numbers they put up either electronically or by hand. And this is really saying it's $3.259 per gallon. But I can't pay them 9/10 of a cent if I buy exactly 1 gallon. Is this just nonsense? Well, because we usually buy more than 1 gallon of gas, I guess if we just bought 1 gallon, they would round up to $3.26, but I usually buy more than 1 gallon of gas. So if I bought, 10.34 gallons and I wanted to know what my total bill ended up being, I would take 10.34 multiplied by 3.259, and I would get a number, and then I would round to the nearest cent, just like I did up here. So I would end up with a number like this that would have a lot of nasty decimals after, nasty numbers after the decimal point, but I would just round that to the nearest cent, and that would be how much I owe. I don't know why it's a big deal if they have the 9 there versus just make it $3.26, but I don't think it's really affecting anybody's um thought process these days. You're not going to drive 2 miles away because somebody, doesn't have the 0.9 cents per gallon or something. Um, but anyway, are there any questions on anything so far? Okay, so jumping into 5.2, we're going to get a start on 5.2. We won't get as far as I wanted, but we should get through adding and subtracting decimals, or at least adding.
Professor, could you scroll
Yeah.
up back a little bit? Sorry.
Yeah, sure.
Thanks.
Yeah, so basically the idea here was this statement is probably a mistake. I mean, I suppose somebody could sell 10 postcards for 0.99 cents for basically 1 cent and then just charge you 1 cent for it, round to the nearest cent, but they probably mean 10 for 99 cents, 10 for about $1. But gasoline makes a little more sense to price in terms of fractional sense because you're usually buying a bunch of gallons of it. And when you kind of multiply things together, like 10 times 0.9 cents ends up being something like 9 cents, and you can actually pay 9 cents. Yep. Okay, so on to addition or subtraction of decimals. Super nicely, adding and subtracting decimals actually procedurally works very similarly to adding and subtracting whole numbers or integers. The most important step here is that we write the numbers vertically so the decimal points line up. This is kind of similar to like if I had 520 plus, 34, I would write it this way so that my ones places and my tens places line up properly. Lining the decimal points up ensures that the place values line up properly. If we need to, we can use zeros as kind of buffers, as placeholders. So we'll see that a little bit later. And then we add or subtract the numbers as if they were whole numbers. And the decimal point just kind of carries straight down. So let's look at an example. 18.37 plus 9.26. We really just add these together as though we were adding together 1,837 plus 926. And in fact, this is the 10th place. This is the 100th place. This is kind of the same as saying I have 1,837 hundredths. And to that, I want to add 926 hundredths. So we kind of are literally adding together 1,837 of something and 926 of that same thing. Those things just happen to be hundredths. So what do I do here? Well, I just add column by column starting from the right. 7 plus 6 is 13. I write the 3, I carry the 1. 3 plus 2 is 5, plus 1 is 6. I ran into my decimal point, I just bring it down. 9 plus 8 is 17. Write the 7, carry the 1. 1 plus 1 is 2. And that is my answer. It's really as simple as that. If we are good at adding together whole numbers and integers, then we're good at adding together decimals. It's the same procedure. If I have a subtraction problem like this, 248.25, and I want to subtract 91.29. Again, I make sure that my decimal points are above one another. I also make sure that I carefully line up my numbers column by column so I don't get everything, crossed up or anything like that. Just like before with subtraction, I do the subtraction the same way. I want to do 5 minus 9, but I don't have enough to subtract that off. I borrow. The 2 turns into a 1. And I get 15. So 2/10 and 5/100 turns into 1/10 and 15/100. So I now have 15/100 minus 9 is 6. I want to do 1 minus 2, but I don't have enough. So I take 1 off the 8 and make it a 7. And then bump 10 more of those over to the right. 11 minus 2 is 9. I ran into my decimal point. I write it down. 7 minus 1 is 6. 4 minus 9, don't have enough. Borrow 1. 14 minus 9 is 5. And then 1 minus 0, that's just 1. I know I'm going kind of quickly through this, but because it's such a similar procedure to adding and subtracting whole numbers or integers, I'm not going super slowly through the procedure because it's the same procedure we should be very used to by now. The main difference is, number one, we have to line the decimal points up in the first place to keep all the place values orderly. And number two, we need to transfer that decimal point down to the answer. That's really the only two differences between adding or subtracting decimals and adding or subtracting whole numbers or integers. What if I want to subtract, say, negative 19.47 minus 32.5? If I was subtracting integers, if I had a negative integer minus a positive integer, I see that my answer is going to be negative, and the magnitude or the size of the answer is going to be 19.47 plus 32.5. Again, this was just the approach that we did when we were adding or subtracting integers. We kind of found the sign of the result. And then we said, since everything is kind of pointing in the same direction, everything is going to the left, so to speak, I could either think of this as negative 19.47 minus a positive 32.5, or I could think of it as negative 19.47 plus negative 32.5. I could think of it that way as well. I know my answer is going to be negative. And operationally, I just need to add 19.47 and 32.5. I don't have anything to fill in the space, so I just add a buffer 0. To the right of my decimal point, I can add zeros, and that doesn't affect the value. I'm going to add these, and then I'm going to make the answer negative. Maybe I'll write that negative number, that negative sign in here now so I don't forget. 7 plus 0 is 7. 4 plus 5 is 9. Oh, I ran into my decimal point. Bring it down. 9 plus 2 is 11. 3 plus 1 plus 1 is 5. Write that a little nicer. And that's our answer, negative 51.97. What if I want to add negative 8.6 plus 9.75. There's a couple approaches here. Probably the easiest approach is going to be to use commutativity of addition. And make this 9.75 plus negative 8.6. And I know that adding a negative is the same as subtracting. So here I'm just subtracting two positive numbers. This is a little easier than having to deal with integers with signed numbers. I know the thing I'm subtracting from, the 9.75, is bigger than the thing I'm subtracting off, the 8.6. My answer is positive. And I just do the subtraction basically as is. I just do 9.75 minus 8.6. Now, again, I have an empty space, an empty block here. I can fill in a 0 at the end of this number, just as kind of a placeholder. I do my subtraction just like usual. 5 minus 0 is 5. 7 minus 6 is 1. Bring it into my decimal point, so bring that down. 9 minus 8 is 1. This gives me an answer of 1.15, or 1 and 15/100ths. So if we're good at adding or subtracting whole numbers and integers, really exactly the same process. We just have to mind the decimal points a little bit at the beginning and in the middle of the problem. But otherwise, the process is very, very similar. And then lastly, what about adding, say, 13.54 plus a whole number, 27? Well, I know that 27, the 7 is in the ones place, so it should mesh with the 3. The 2 is in the tens place. It should mesh with the 1 that's in the tens place of the 13.54. But I know that 27 has 0/10ths and 0/100ths. So that's really just 27.00. So I can I can append zeros to the right, but I have to make sure they're to the right of the decimal point. And if I don't see a decimal point, I can put it in to the right of the ones place. So 27 and 0/10ths and 0/100ths. 4 plus 0 is 4. 5 plus 0 is 5. We ran into the decimal point. My decimal points are a little wonky here, but there's our decimal point. 7 plus 3 is 10. I write the 0, carry the 1. 2 plus 1 plus 1 is 4. That's 40.54. So adding, subtracting decimals, super easy as long as we make sure to line things up properly in the first place, getting the decimal points lined up in the first place. And as long as we remember to just bring it down when we're going along right to left and we run into it, just copy it straight down and keep going. And that's really all there is to adding and subtracting decimals. Works super nicely. Right. So if we're adding and subtracting parts of wholes, like would we remember decimals are very similar in theory to fractions? Would we rather add parts of wholes that are fractions or rather add parts of wholes that are decimals? Probably decimals, right? If I'm adding or subtracting, I'd much rather deal with decimals than fractions, almost all of the time. Right, fractions had the whole like getting a common denominator and all that kind of stuff that we had to do and simplifying. But decimals, we just add them like they're whole numbers and just mind where the decimal point is. Okay, so next time we come back, we will talk about multiplying decimals. And this will actually work pretty similar to multiplying whole numbers, but we'll have to be a little more careful with the decimal point. We'll have to do a couple different things with the decimal point, but will still work pretty similar to multiplying whole numbers. Okay, let me stop the recording.